So integrals show up with limits, and both with limits and both without limits. So the integrals we've been working with, we call definite integrals because they evaluate to a number. They represent a change between those two numbers, how much the function that the thing you're integrating tells about, how much that function actually changes. The thing you're integrating is a rate, and it's the rate at which something changes. So outside of a word problem, none of that really matters. We're just really doing the integration. When we don't put limits there, we are really just trying to find the function. We're kind of working backwards to find the function. We're really just finding an antiderivative. But with indefinite integrals, we're going to just kind of notate that there are multiple functions that can actually give us this same derivative that is the thing we're integrating. If you remember back to the day we used colored pencils, we found 4 antiderivatives of the same function there, and they were all just horizontal shifts of each other. And that's really what it comes down to when we do an indefinite integral, is that we want to just represent the fact that we know the shape of the curve, but it can be horizontal or vertically shifted. I said horizontal before, sorry, wrong word. Vertically shifted up and down from just sort of the base curve that we find. We do that with just literally, we're just going to add something to the end of it. We're going to add a variable to the end of it. That variable is going to be c, and we refer to it as a constant of integration. So with all those words, here's what we do. If you have an integral without limits, you find an antiderivative, and you are 99% done. So following all the normal stuff we do, what's an antiderivative for x cubed? Yep, x to the 4th over 4 minus, and what's an antiderivative for 4x? 2x squared. So that is an antiderivative. The answer to the indefinite integral problem is to put a plus c at the end of it. That is some number that either raises if it's positive or lowers if it's negative the function. So proper notation for just an integral without limits is find an antiderivative and add a plus c. That's 3/4 of the new stuff for today. Okay, let's look at a couple more examples. Really just to review antiderivative properties and see some other algebraic things we might want to do here. Number 2 is e to the 4x. We're trying to find an antiderivative for that. Remember, these rules are related, especially the simpler rules. E to the 4x would be a linear chain rule problem with derivatives. It is a linear chain rule problem with integrals, but we're working in reverse, so we have to do the reverse thing. When we take the derivative, hopefully we're really good at just dropping that 4 out front. But when we're integrating, instead of multiplying by 4, we divide by 4. So the answer to this one is 1/4 e to the 4x, and then plus c. I know somebody I was talking to yesterday in tutoring, same rules apply. Arguments never change. This is a process that we can work forwards and then backwards with. So if when you're taking the derivative, the argument never changes, then when you work backwards, the argument still can't change. Otherwise, it would have had to have changed in the other direction. So arguments still never change. If you're integrating e to the something, you're going to have e to the something still there. That same something still there. It's never correct to integrate the 4x or anything like that. All right. 3 and 4 are really just using rules of exponents. We will do, number 3 is kind of like a preview of a problem that we'll do a more complicated version of in Unit F. But the rules of algebra allow you to break this up into 3 separate fractions, all with x as their denominators, and then you can just simplify. So the full version, you probably don't need to write out this in this many steps. This is algebraically equivalent to 3x squared over x plus x over x plus, and by plus I mean minus 2 over x dx, which is equivalent to just the integral of 3x plus 1 minus 2 over x dx, which is just 3 power rule problems. You have x to the first power, you have a constant, and you have x to the negative first power. So I guess that last one is not power rule. Okay. So in antiderivative for 3x, yep, 3 halves x squared. Antiderivative for 1, x, yep. And antiderivative for 2 over x. 2 ln absolute value of x, right? Yep. Just another good time to say this. The only time that ln pops up is when the denominator, when the thing in your denominator has an exponent of 1. Okay? So one of the things that I know from past experience, and I've seen it 1 or 2 times on the most recent quiz that we took, if this were 2 over x squared, ln doesn't show up there, it's power rule. If this was 2 over square root of x, ln doesn't show up there, it's power rule. The only time ln pops in is when you go to use the power rule and you say to yourself, okay, so I've got to add 1 to a negative 1, that's 0, but then I have to divide by 0, which doesn't work, right? That's the whole key. The power rule fails on this one, so it does turn out that it's not a power rule problem. That's the only time you wouldn't use the power rule. Okay, so that is algebraically equivalent with dividing. The next one's going to be an algebraically equivalent statement with multiplying. So I'm going to, in number 4, basically just distribute that 3x in to get myself in the same place I was in number 3. So I'll, again, draw too many steps here. I'm going to rewrite this as 3x times x to the 1/2 plus x squared dx. You know, that one could happen in your head for sure. But now I definitely see the numbers I need to work with.
Sorry for the interruption. Ms. Henry, please call extension 81412. Ms. Henry, 81412. Thank you.
Still integrating. X times x to the 1/2 is x to the 3/2. Yep. And then obviously, I've got to multiply 3x by x squared. That's going to be plus 3x cubed. My equal sign looks like a minus. What's that? Okay. Another just word of caution, maybe not specifically in this problem. That step that I did in both spots in 3 and 4, sometimes feeling like you did something makes you think you've integrated. So another mistake that I sometimes see is people will distribute and they'll be like, okay, I did something, so I can get rid of the integral symbol. But if you haven't, I mean, obviously, it's obvious when you think about it. If you actually haven't used the power rule, then the integral symbol needs to still be there. So just a goof that I see people make sometimes, and as soon as you tell them, like, oh, yeah, of course, I never actually integrated. Okay, so 2 power rules. The trickier one first. X to the 3/2. When I raise that up, I get 5/2. Yeah, so 5/2 is my new exponent. Sorry, I guess I could have asked that better. Which means that I need to divide by that or multiply by the reciprocal. So 2/5 times 3. So I end up with 6/5. 6/5 x to the 5/2. And then plus not just 3x to the 4th, but over 4. Yeah, over the new exponent. So 3/4 x to the 4th. And then since we've got an indefinite integral plus c. So the only thing that's new, we say what's an antiderivative? This is the indefinite integral. The plus c at the end could be any number. It represents the fact that there are an infinite number of functions that actually give us this original derivative. And any function in this form with any number in the world there, when you take its derivative, gives you that guy. All right. So, time for the must-knows. Most of these are relatively straightforward, but these are the ones that will show up on your test. So x to the n dx, we're going to basically just increase our denominator or our exponent by 1 and then put it in the denominator. So I can either do it this way or just make it a fraction. And then don't forget your plus c on every one of these. Actually don't think this is on your review sheet. I didn't realize these didn't match until I was just doing it. I don't want to make this a must know. I'm going to cross this out and put the one that is on your review sheet, which is the integral of a dx. That's on. Oh, okay, perfect. Was it in the same spot? Yeah. Gotcha. You know what? I did open up a slightly different. This one said E8, so I looked at the problems, but I didn't look at this. Okay, cool. So yeah, so that's what you have. That's what you have there anyway. Perfect. A is a constant, so we end up with ax plus c. I do want to put one more thing on the first one that I just remembered. I do want to put n does not equal 1 here. And just kind of clean that up for my benefit. So it's that works whenever n doesn't equal 1. And we will have the situation where n does equal 1 a little bit later. Alrighty. So the third one is the linear chain rule problem. If you integrate f prime, you are going to get f. Oh, I knew I felt like, thank you. Yep, I cleaned it up. Because you would end up dividing by 0. You're right. Thank you. Perfect. I think I felt like I could just autopilot these, and I don't think I can. All right. Yes, n cannot equal -1. All righty. Integral of a dx is ax plus c. When you integrate f prime, you get f. The argument can't change, but what do we have to multiply this by according to the linear chain rule? Not a. But that would be a. 1 over a, because we're integrating. I did say, what do we have to multiply this by? So it's 1 over a times f of ax plus b. Right. When I integrate sine, I get negative cosine. And again, it makes sense, because if I then took that thing's derivative, I'd get that negative to cancel out. Directly under it, then, when I integrate cosine, I get positive sine. Yep. What gives me secant squared when I take its derivative? Question? Yep. You need plus c on all of them. Yeah, so yell at me anytime I forget it. I just ran out of room there. Tangent. Yep, this is tangent of x plus c. And directly below it is positive. If I take the derivative of cosecant, I get negative cosecant squared. So it's negative. So it's just, again, the way they work out, the cosine and sine have swapped where the negative goes, but these one, it matches, because they don't go to each other. I think they're not kind of looped. Like sine and cosine are looped together, but tangent and cotangent are, their own separate functions that go to their own separate co-derivatives or antiderivatives. So in the same vein, you got my plus c's there. Secant tangent, what gives me that? Secant x plus c. And cosecant cotangent, for the same reason as the other one, will be negative cosecant x plus c. All right. And then, you'll notice that the difference between these must-knows and the must-knows that we did with derivatives is we're not just saying what are the integrals of the 6 functions. We're actually looking at the results of the derivatives of those 6 functions. So things like, trying to find out just an antiderivative for tangent, we'll do that somewhere in the next section, but we would have to use u sub. It's not a must-know. I'm not even sure if there is. I think the derivative for just plain old secant, which again isn't listed here, you probably need to do something like integration by parts, which is not for AB. So, all right. Couple more left. The integral of e to the x is e to the x. It's its own derivative, which makes it its own antiderivative. Remember, a to the x is not the power rule. There's never a correct time to do like a to the x plus 1. You're changing an argument if you do that. X is the argument in that one. It works just like a to the x. When you take the derivative, it's ln a times that. So when you integrate, we're going to do 1 over ln a. Remember, this is a coefficient. So if you think about what you're putting there, because there's always the, oh man, is it a or is it x that goes there? If you put 1 over ln x, you've got a function. If you put 1 over ln a, you just have an ugly number. All right, a couple more left. When we integrate 1 over x, here's our n equals -1 case from above. Obviously, and if you just put it in terms of x, we get ln absolute value of x. Put my plus c where I missed it. Put my plus c where I missed it. I mean, this is just, I know, I was just pointing out that this was the missing piece from over here. You can't use the power rule here, so you have to use this rule instead. That's all. Nope. Just kind of a thought bubble. N equals -1 from above. You don't need to write that on a must know. And then this part's nice. We only need 3 of these. What gives us the derivative in the lower left? It's 1 over, but sine gives us cosine. Okay, gotcha. Arc inverse sine or arc sine x plus c. This one's secant with the absolute value. Secant x plus c. Arc secant plus c. And then, of course, the last one has to be arctan. And we actually don't need antiderivatives for arc cosine, arc cosecant, or arc cotangent, because if we put them there, this is what we would have. So if I wanted to write the corresponding integral for arc cosine, it would just be -1 over the square root of 1 minus x squared dx. That would be arc cosine of x plus c. But I could also do this. Just say, hey, it's -1 over the square root of 1 minus x squared dx, and say that that's negative arc sine x plus c. And they are both valid antiderivatives, but why put 3 more must knows there? The smarter thing to do is just to use negative arc sine x plus c. And a little bit of a picture to kind of go with that, taking a quick look at Desmos. If I do arc cosine, I'll probably find that in functions easier. Yep, arc cosine of x. And then I do the same thing, but negative arc sine of x. They're just vertical shifts of one another. So if you solved a problem using the antiderivative cosine inverse, and somebody else solved the exact same problem but used sine inverse, you would find that those c values, and that's where we're going next, is actually solving for c values. Your c values would be different because you would have to, if you were using this one, your c value would have to be this much lower than the person using the purple one. So they are the same shape. You would just have to change your vertical shift. So it does not matter which one you use. So why learn 3 more or put 3 more on there when we don't need them? All right. Okay. All right. So here are the problems that we would use for where we would use indefinite integrals. We want to get the antiderivative that matches some situation. So we have a derivative, but we want the function. We want to know what function gave us that derivative. So we need 2 pieces. We need the antiderivative, and then we need a piece of information about the function. So I need that function's value somewhere on it. And once I have that, I can use it to basically just plug in and solve for C. That's going to be this is going to be really the only new thing today. We're going to use this last piece of information to solve for C. What we're doing here is what we're going to do in Unit G, which is called differential equations. It is its own separate topic in math. There are classes in high school called differential, or classes in college that are called differential equations. So, you know, in unit G, which is our by far shortest unit, we're just going to put our toes in the water of differential equations. But that's what we're doing. We're solving a different differential equation. We have some sort of derivative, and we want to work backwards to find what f is exactly. What is the antiderivative that matches our situation? So we are just going to do what we did on the front page. We are going to integrate f prime of x to get f of x. Nothing too difficult here. E to the 2x when I take an antiderivative is over 2, yep, or 1/2 in front of it. Either way is fine. And then we'll do minus 2x cubed over 3, so 2/3 x cubed plus c. So that is showing the proper notation. If I write an indefinite integral, I have to say, you know, it equals the function plus c. And I can also then say that f of x equals this. If you integrate an f prime, you get back to the f, but I don't know what that c is until I do this. The f of 0 equals, plug 0 into your antiderivative. So 1/2, e to the 0 is 1, minus 2/3 of 0 cubed is 0, plus c. So we know that the f of 0 equals that by plugging 0 in. We also know that the f of 0 equals 4. Yep, 3.5. So your answer on that one would be get rid of the 0, subtract 1/2 from both sides, c equals 3.5. So the function, the antiderivative that matches our situation is 1/2 e to the 2x minus 2/3 x cubed plus 3.5. And anytime you're in a simple situation like this, that's all you need. You just need the function value somewhere, and you're basically essentially then just moving the curve upside down, up and down. Now, where do I have to move the curve up or down to get it to be on that one single point? And then the rest of the curve will just follow it. The only difference in number 2 is just a little bit of notation. So we have dy dx equals 2 over x plus 6x squared. So we need to integrate that. A little bit about the language of integrals. This is just a quick introduction to this that we'll talk about a little bit more when we actually get to unit G. What we're going to do here is we're actually going to separate our dy and our dx and move them over. So we're going to integrate dy on one side, and then that's going to equal 2 over x plus 6 over x squared. Sorry, I should have drawn the integral symbol, dx. Yes, and I like to put it that way because we're not doing something mathematical. We're changing from the language of derivatives to the language of integrals. So with integrals, we have the dy and the dx on separate sides. But with a derivative, we keep them together in the fraction form dy dx. When we integrate dy, we get y. We could put y plus c there, but we only need it in one spot. It doesn't give us any more by putting it on both sides. Again, something we'll talk about a little bit more in unit G. We should end up with 2 ln absolute value of x plus 6 over x squared is going to turn into, when I integrate, negative 6 over x, because you're going to take that negative 2 and pop it up by 1 to negative 1. And then dividing by negative 1 just makes the sign negative. So minus 6 over x plus c. Okay. And then we'll end up with, we'll call that f of x, just for notation purposes. So then we'll do the same thing we did in the other one. F of 1 equals 2 ln of 1 minus 6 over 1 plus c equals negative 7. But 2 ln of 1 is 0. So basically we have minus 6 plus c equals 7. Negative 7, sorry. Which means that c equals negative 1. Yep. So in this case, our f of x is 2 ln x minus 6 over x minus 1. Right. Yeah, there's one more thing I should be talking about here, but really is a unit G thing, so I'm going to leave that answer. I just need to say it out loud. I'll leave that go. This function has discontinuity, and we actually have to write it so that it's only one side of the function or other, but we'll deal with that in unit G. All right, last but not least here. We have 3 and 4 to do. 3 is actually a relatively simple one. Just be on the lookout for ones like these. This happens a lot where f of 1 looks really complicated, but it's actually going to make the problem a little bit easier to solve. So f prime of x is 2 to the x. That means that f of x is the indefinite integral of that f prime, which is still 2 to the x, but the coefficient is, no. You just said ln2, right? 1 over ln2. Yep. Boom. And then, of course, plus c. And we know that the f of 1 is a different problem. There we go. The f of 1, it's mad at me. Okay. Let me do that. And let's just come back into it and see if that changes anything. Yep. Yeah, let's come over. Oh, it turns out it was all there all the time. It just wasn't showing. Okay. All righty. Try that again. It should work now. The f of 1 is 1 over ln2 times 2 to the first power plus c. And that equals 2 over ln2 plus 5. I mean, other than just a little bit of notation, get rid of that 1, bring the 2 to the numerator. These two things are the same, which just makes c equal to 5, right? Subtract 2 over ln2 from both sides and they're gone. C has to be 5. Okay. Take a look at that last example. Two important differences there. One of them is, it's f double prime. And then the second one is we actually have a value for the antiderivative. So this is a good, simple example. This one isn't super difficult, but we are going to, if we know f double prime, that means we need to integrate twice to get back to f. That also means that each integration along the way is going to give us a c value, and those c values are different. Like it's not just the same c value each time. So we've got to solve for each c value along the way and then use those c values. So looking at this for f double prime, we'll recover f prime of theta by integrating f double prime of theta. I'll actually write that out this time. D theta. And theta is just taking the place of x, which means we'll integrate sine of theta, d theta, to give us integral of sine is negative cosine. All right. So I know that f prime of theta is negative cosine theta plus something. So let's find out what that plus something is. And I'm actually going to go ahead and label this C1, knowing that I'm going to have multiple C values and I need to distinguish them. So f prime of 0 is the negative cosine of 0 plus C, and that equals, according to the problem, negative 1. What's the cosine of 0? Nope. That's the arc cosine of 0. It's 1, yeah. Cosine starts out 1, sine starts at 0. So yeah, so that actually is just -1 plus C1. Sorry, I got to be better at doing that. -1 plus C1 equals -1. So C1 is 0, yeah. Just for space, I'm drawing that arrow there. So that implies that C1 is 0. Which actually makes our next step a little bit easier, because if that C1 was a value, in my next integration step, I'm going to get an antiderivative for it. Because like if it was like a 5, I'd have to integrate that 5 to get 5x. But this example, it's relatively easy. So now I know for certain that f prime of theta in this situation is just negative cosine theta, which means that to recover f, I'm going to integrate that negative cosine theta d theta. Negative sine theta, yep, plus c. So we'll write C2 this time, and I won't forget. All right. I forgot. It's, yep, cosine theta d theta. And we know that the f of 0 is -4. So negative sine 0 plus C2 equals -4. But the sine of 0 is 0. So C2 equals -4. So we now know that the f of theta is, where are we at? Yeah, f of theta is negative sine theta plus C2. So we've got negative sine theta minus 4. If C1 was a value, then there'd be a third thing here. It would be negative sine theta plus, like, let's pretend this was 5. You'd have negative sine theta plus 5x plus or minus something. So you would actually recover a term each time along the way. Yeah. So it is, when you just don't lose that when you do. Hopefully there's a practice problem where that happens. I know I got this problem from somewhere, and it's kind of weird that I should have it set up so that the C2 comes out to 0 instead of the C1, so we actually see that. But yeah, Maya disagrees. All right, guys. So that actually is everything for this one. So we have the remainder of time to work on this one. We've got a short period tomorrow, so we won't move on to anything new. So some time to get some things done. Utilize it wisely. And then we take 3 days on U substitution. Jack will not be. We may have